Without further ado, Dr. Ed Overton is a professor in the Department of Environmental Sciences, School of Coast and the Environment at LSU. His research interests include understanding the fates and distributions of hydrocarbons following an oil spill, the environmental chemistry of hazardous chemicals, and the detection of environmental pollutants at the site of sample collection. He's been active in understanding the fate and effects of petroleum hydrocarbons in the marine environments from oil spills since 1978. Is that okay? He's held the Claiborne Chair in Environmental Toxicology and Air Quality prior to his retirement, and was honored as an LSU Distinguished Faculty in 2008, and was the 1996 Louisiana Technologist of the Year and the 2010 Louisiana Communicator of the Year. And one fun fact is that he's a celebrity because he appeared on the Late Night Show with David Letterman.
The crowning achievement.
Yes.
Can you put up the slides? Charlie mentioned that we're chemists. I'm an environmental chemist, and Charlie followed in my footsteps. So I want to talk a little bit of chemistry, and it's a so what for oil, and that leads to why to burn, and the chemistry determines if the oil is capable of burning, because certain oil residues just don't burn very well. They're very thick, and if you squirt them in a boiler where you got good mixing, they burn, but out in the real world environment, they don't. So first idea is, what does oil do that can cause problems? And this slide kind of shows it, and really you're concerned about these three big issues, right? Oil contains some compounds that are toxic, and they are ingested by most animals, not all animals, but most animals that have enzyme systems. They oxidize those components, and that causes those components to be toxic to that organism, right? So you've got toxicity, and toxicity always goes with how can it get in you. So you've got toxicity and routes of exposure. Those are the two biggies, and those are the ones we worry about a lot. Virtually all the compounds in oil can be degraded in Mother Nature by natural organisms, and that degradation uses up oxygen. And particularly in the coastal areas where you don't have a lot of oxygen in the summertime in hot marshes, you're using it up. We call that biological oxygen demand. We're dumping a lot of chemicals in the coastal areas, using up the oxygen, and then of course all the animals that need oxygen are expiring. And then the last is smothering and coating, and we've seen pictures of the pelicans coated with oil. Pelicans, any of those animals, including, I don't show it here, but the leaves of these coastal plants, right? A leaf has a function. It takes in sunlight and carbon dioxide, and it gives off oxygen and water. If you coat that leaf, it can't work, right? So you've got coating of plants as well as coating of animals, and both of those are bad. So these are the three biggies. And what you want to do in an oil spill, what people can do to the extent possible, is to limit all of this stuff, right? So that is the reason for in situ burning. It's the reason for dispersion, and it's the reason for skimming and mechanical removal. Let's see. Do I move these things forward?
Yeah, there's a point up there. Sorry.
There's a pointer.
Yeah, you see the arrow.
All right. Okay. This is you hear us talking about weathering. Oil that goes in the environment immediately starts changing its chemical composition. And this is this window of opportunity that Charlie talked about. As this composition changes, its ability to be dispersed and skimmed and all of these other things change with it. So what happens is oil enters the environment, and some of the components in oil immediately partition into the air or the water, and then you've got the residue. The residue is what we see. We call that oil. It's really an oil residue. It's not what came out of the ground or out of the pipe, because this happens pretty quickly, the volatile components. Now, what happens? This stuff can be ingested by organisms, so there's your route of exposure. So this is where the danger occurs. Not many animals are going to be eating the oil. So chemicals that are in the oil are safe from ingestion. Chemicals that leave the oil are available for the organisms that live there, and they're available for natural bacteria to degrade them. So this is where the degradation and the problems occur. But what happens is that this residue loses these volatile components. It is reduced in size, but it's also reduced in its chemical properties. These things, this is a solvent. These are liquid components, and as these liquid components evaporate off the oil, you're left with a more waxy, sticky residue. And ultimately, we know that when all of those components leave the oil, then you got a solid mess. Asphalt roads are an example of that, tar balls and residue balls. So as oil goes this way, you lose your opportunity. This is the most dangerous form of oil. It's when we can do most with it. We can disperse it, we can burn it. We've got a lot of these components. By the way, oil doesn't burn. Chemicals that are released from the oil into the air burn. In order to burn, you've got to mix these chemicals right here. You can heat them up a little bit with a match, but you're evolving them into the air. They mix with oxygen, and that's where the combustion occurs. So oil doesn't burn, chemicals released from the oil burn. As we lose those chemicals into the air and the water, this stuff becomes much more viscous, much more difficult to burn. So if you want to, and by the way, that's the time when the oil is most dangerous to the environment and the people. You got volatiles coming in the air, these can be breathed, and a lot of those volatiles will make an explosive mixture. The last thing you want to do over a big patch of oil is go out there and start throwing a match around. You got to know what you're doing or you will be part of the oil spill, right? And of course, that's not what we want to do. Well, this, Charlie mentioned Al Allen, and this is Al Allen's figure, and I thought since we're following this up with a talk on dispersants, I would mention, but Al came up with the idea of aerial coverage, and what we're talking about is this kind of time frame and thickness over here. I'm not going to spend a lot of time on that, but suffice it to say, when you've got aerial dispersant coverage, you can encounter the oil at a lot larger rate. This is a logarithmic scale here. So this is the kind of area the oil has to be thick enough to burn. A sheen won't burn, so you can't go out there and do the sheen. You got to have approximately a millimeter or two of the oil. That's why you concentrate it in the booms, and you get it concentrated enough, and if it's still volatile enough, you can add an igniter, strike a match, and allow it to start to burn. So as oil changes, remember we're talking about reasons to in situ burn. You want to remove that oil so it will not affect environmental concerns, and most people think the largest concentration of environmental concerns is coastal marshes, right? Of all the places along the coast that's most susceptible to damage from oil spills, coastal marshes. And of course, in the Deepwater Horizon, we had a major oil spill lasting for almost 90 days, right next to the largest concentration of coastal marshes in the country, right? So as oil weathers, it goes along here, your offshore response options effectiveness gets less, right? So if you're going to respond to either burning or dispersing, you got to do it in here. Don't wait till you get down to things that have an API gravity of 10. By the way, this is really, really thick molasses, and this is a little bit less volatile than gasoline, right? So you want to work in this general area down here rather than just general area. Notice that all of these things follow this kind of same parameter. Once you get here, you know, you're shoveling it up. You're not dissolving it in causing it to disperse or being able to burn it. You're shoveling it up, whereas you have options here in terms of dispersing the oil. I just want to mention that I've already said this, but if we look at the largest environmental impacts, I mean, we can get in here with heavy equipment and clean that beach up. The biological density along that beach is not nearly what it is in coastal marshes. So coastal impacts on sandy beaches are severe, but they're more economic. Nobody wants to go swimming on that beach. Not many people are going to sit there looking at it. But up here is where you're going to get severe environmental impacts. And this is the reason why we use all of these procedures offshore. You want to prevent this to the extent possible. Al Allen would be the first person to say that none of these remedial techniques are 100%. So if you get 50% removal, it's a really, really good day. So no human-induced activities are going to remove all the oil, but we can lessen the oil. And of course, what we want to do is protect our environmental responses. Now, here's some of Charlie's pictures that he couldn't get off his computer. And again, this is the nighttime burnings. Each one of these burnings involve collecting the oil. And here's the collection up here. Notice that you've got a vessel here that's in the back that's going to ignite it, and then you've got two tugs out here pulling the thing. They have to be long enough toes to be out of harm's way, because once you concentrate the oil in here and ignite it, that's what it looks like. That's the process of in situ burning. And of course, the products are the soot and the byproducts. When you're burning oil, has aromatic compounds, and every chemist knows that aromatic compounds give a lot of sooty flames as opposed to like charcoal lighter. Charcoal lighter has been de-aromatized, and when you light your charcoal, it doesn't have a lot of soot in it, right? So oil burns, gives off this, and there's a residue that will be left in these booms. And here's a picture of the residue that came up on the beach, and this is the Royal Reds. And Charlie mentioned this Our Mother cruise, which is the name of the shrimp boat, and it had globs of this oil down in it, and this was well after there was no visible oil on the surface, right? The oil had gone. Another picture of what some of these globs look like. Again, this is down on the water, and this is in the water. So if you say it's in the water, you mean that it's no longer lighter than water in its capability for floating. These things were collected in deep water with the trawls, so obviously they are not floaters. That's one of the problems with in situ burning. Some of that oil that you burn is going to end up on the bottom. You just want it to be as minimal as possible. That means you want it to have the hottest fire burning in the burning. This is the composition. It's a gunky, not particularly dangerous. You could clean that shrimp off and eat it, but that nobody is going to buy it, right? And so that's your advantage in these types of residues. What about the chemical composition? This is some of the research. Again, I don't want to get too geeky chemistry on it, but this is the shrimp trawl, and this is the density, the average density of something like, what is that, 24 samples of tar that we got from these various shrimp trawls. And notice that the average is 1.04. The density of seawater is 1.03. What that means is this stuff is heavier than water, and when you put it in water, where is it going? Kaploop, right? Really, really, really hard to get oil on almost any remediation, normal oil like the South Louisiana crude, to sink. I mean, we've tried to do it in the lab, we've weathered it, it just won't sink. We figured a way to make it sink, this burning residue. So that's one of the downsides, and that's one of the things you have to take into consideration. You know, is that going to cause a problem? The good news about those tar balls are that they don't dissolve. All of those dangerous components have been boiled away, so you got a glob down there. So the impacts were the perceived impacts of contaminating those fish trawls and the costs associated with that. They're also very high in asphaltenic content, and of course, what the reason for that is that the burning gets rid of all of the other components in oil, and you've got this globby stuff, which we, in fact, when we refine it, we can't do much with the residue, and so we mix it with sand and rocks and put it on the road, right? So that's what it looked like. Chemistry, it looks a lot like, this was an example of these oils right here. The chromatogram, I just want you to look at that little point, This is assimilated distillation. So basically, you take oil and you heat it up. This is how the engineers that run refineries look at the oil. This is the same oil. Notice that it doesn't have that little tip in there that Mother Nature degraded the oil. This was a tar ball, but not from an in situ burn. So chemically, we think we can be pretty good at identifying if an oil residue that we collect in the environment came from in situ burning or from natural degradation and things like that. How much time have I got? I'm almost out of time. So I guess the bottom line in what I wanted to say was, This is where a lot of activity occurs in terms of the biological productivity for the entire northern Gulf of Mexico fishery. It's up in the marshes. That's where all of these lifestyles, the nursery grounds for a lot of these organisms, feed organisms. I'll show you an overview. So what you want to do is to try to get rid of the oil out here where you have very little biological density. There of course, are animals that have a lifestyle just on the surface. There are turtles that have to come up, the marine mammals, all of those things. But the density of life, as any fisherman knows, you've got to go to areas where the biological activity is concentrated. Where is it concentrated? Natural reefs, drilling rigs, places like that. That's where you go to fish. If you go out there and just throw a line in the water, you're going to use a lot of gas and not get many of those fish, right? You've got to know where you're going. And so what you want to do is to try to remove the oil here to the extent possible before it gets up in here and starts doing a lot more damage. I did always throw a bunch of extra slides in because I found out I was supposed to give this talk yesterday and I wasn't sure what I was supposed to talk about. So I always throw in 10 or 15 other slides. But this is a diagram of what happens when oil comes ashore. You know, this is a sandy beach, and I'm going to show you a coastal marsh in a minute. But you've got this bar out here, and that bar causes oil that floats in to get mixed in with wave action and hits detritus in this intertidal area and causes a lot of this oil to sink. These are the tar mats that were found, and you can see that tar mat over at Gulf shores. Some of the oil is put up on the shoreline, and you get these surface residue balls or whatever, the tar balls or surface residue balls. But the good news is you can bring in heavy equipment and you can clean up those things from beaches contaminated with oil, right? So the remedial options are much greater on a sandy beach. However, if you've got a coastal marsh, you don't have offshore this little offshore bar. The oil, this is the high tide mark, low tide mark, and it floats in. And so this is what a marsh would look like. And when the oil came ashore, notice that it coated the first 10 to 20 meters of oil. You've got this sticky absorber there, right? The leaves. And when the oil floats in at high tide, it's in a marsh, it's actually, the ground level is coated with water. So the oil comes in and sticks on this area, and that's where it can cause damage. And the trouble is that this is very, very mushy environment. You can't go in and stand on it and do much with it. So here's an example of trying to wash it off. And this is, what you don't see here is a barge offshore pumping this water and trying to rinse it off. But you can't put heavy equipment on the marsh and not do more damage than the oil would do, right? So your remediation options are pretty limited once it gets onshore. So the point is, if you can do something with it in the deep water, disperse it or burn it, and I hope I'm leading into the dispersant discussion here in a second, that's what you want to do. You want to protect these areas from death. Again, I'm tooting the reason for why we're worried about our coastal marshes. I'm a chemist and I learned a lot by listening to all my biologist friends. But you've got the primary producers are things that take carbon dioxide out of the atmosphere and make biomass, food, right? Cows eat the grass, so they're not primary producers, they're secondary, they're primary consumers. So these little microorganisms, all of those live up in the marshes. And when the oil comes in and that water, those chemicals dissolve out of the oil into the marsh, that's where you have routes of exposure and can cause damage down here, right? So that's really dangerous. We do not want fresh oil to come ashore. Fortunately, in the Deepwater Horizon, the oil spill was well offshore, and a lot of the volatile compounds had already been lost for a lot of the oil, and that certainly limited the severe damage from the Deepwater Horizon. Had a spill of that magnitude occurred closer to shore where a lot of the fresher oil came ashore, we would have seen much greater damage. But the point is, do something well offshore to protect these coastal resources. How am I doing here? Almost out. Let me just run through some pictures. Again, we've all seen these pictures of coastal marsh oilings. This is the mechanical arms I mentioned. But look at, I just wanted to show you this. This is an unimpacted marsh shoreline. See how smooth it looks? Now look up here, both of these are satellite views of the first 10 to 20 meters of that shoreline was covered with oil. Now you don't see any oil, right? But notice how rugged that coastline is. It's not smooth like this. And what happens is that Mother Nature smooths it out. Another way of saying that, this ragged area is washed away, right? We call that land loss, coastal marsh. So that's another reason. It's not just the biological activity, but the effects on the geology in the Exxon Valdez. You know, we had oiling of rocky beaches. And baby, you weren't going to move those rocky beaches. I mean, the rocks on there, we see a rock down here, we think, you know, a little pebble like this. So you walk on a rock that's that big around, you can barely lift the bloody thing. So the geology didn't change in the Valdez, but the geology definitely changed, and we speeded up a process that's already occurring. 15 seconds. I would like to say that there are some unexpected consequences of oiling on the shoreline. It's hard to see, but if you look right there, that little red arrow, this is a plug that was pulled out of the ground. Now, that's oil residue that's on the ground. It's covering up. All of the toxic things have been leached out. It's just sitting there. It's ugly. But this oil seeped down in fiddler crab burrows down into the ground because it comes on shore. The tide goes down. The oil is hot. It dissolves down. And so there are areas like this of buried oil. And this buried oil still has those volatile compounds that can cause damage, right? So they are residues, and they're in our coastal environment. The good news is that not many of them, it's not nearly like it was in 2010, but they will be there for a long time, and eventually, as this goes to leach out and cause some very lingering, very small levels of long-term monitoring. And it says that I'm at the end. These are where the in-situ burns showed. So Charlie and I would be happy to answer questions. Where did Charlie go? He can't run out the back.
We're gonna do a question and answer panel after.
Okay, question and answer.
Yes. So you guys want to stick around?
Okay, yes, thank you very much.